So today's class, we're going to start modeling now, and the main method we're looking at will be supervised learning. Supervised learning. So like we normally do, the quote of the day says, data really powers everything that we do. Data really powers everything that we do. This is from Jeff Weiner, the CEO of LinkedIn. I chose this quote just to give us a mindset or a perspective that when you start implementing models, you're going to find that you need data to start building those models. And also, the culture in Nigeria now is not really strong on keeping data. There may be some large corporations that keep data because storing data is actually very expensive, right? But so if you want to start implementing projects for companies or for consulting for big firms and all that, one of the limitations you may find is data. So we need to really start having that culture of keeping data and then applying the data for modeling to get more information. So data really powers everything that we do. So today we'll look at the introduction to supervised learning. We'll just introduce modeling with just a simple linear regression model.
Sorry, sir. Sorry.
Yeah.
I'm so sorry, sir. I'm so sorry to interrupt, sir. I just wanted to ask because it has been a question on my mind for a minute now, and then you just talked about how that is very important, and I'm just like, if somebody were to ask me, if maybe, for instance, you talked about wanted to do a project for somebody, and then we're finding it difficult to get data. So, like, how do you tell somebody, like, how is data stored? First things first, like for instance, I don't know, is it like there's a mechanism in their so-called system that just keeps all those data naturally, or they have to like do some work, or like, because I don't know, I actually don't know. That's what
Okay, so that's where it's a good question. That's where data engineers come in, right? But it depends on the kind of data. So there are different ways for storing data. So the data engineer can create a pipeline such that when information comes in, you can store in a data warehouse or a database. So there are database platforms like PostgreSQL, database platforms like Teradata. Teradata is a data warehouse. Platforms like Google Cloud, BigQuery, AWS, S3 Bucket. So don't worry about knowing what these names are. I'm just saying there are different platforms where data can be stored. Like if you watch Netflix, okay, I think YouTube is more common than Netflix. If you watch YouTube, for example, the YouTube stores your data once you come on the platform. So when you watch a video, if you go back to that platform, that's if you log in though. YouTube can recommend you videos for you based on your watch history, right? So those activities that you do on the platform, what video did you just watch? Watch. How many minutes did you watch it? The data engineer has set a pipeline such that it collects that data and then it stores it on their data warehouse or their data base, right? So there has to be a system of collecting the data and storing it. If it's just a simple problem, like I think like healthcare, for example, where nurses will come to check the person's blood pressure, sometimes they document it, sometimes they don't document and all that. Simple cases, they may just record it in Excel and save it as a CSV file and all. But if there's a lot of data, then like banks, for example, they will store it in a database. Yeah, I hope that answers your question.
Yes, so this all this whole system for like big corporations that they can't like have to do it themselves. It will be automatic, right?
Yes, it
Like,
has to be automatic. Yes. So that's what you call data pipeline.
that's not in our jurisdiction, I believe.
No, that's the work of a data engineer. So the data engineer kind of helps us get the data available to us. Then we can collect that data, combine the data from maybe different tables. then analyze that data to build a model. Yeah.
All right,
So that's
thank
Sorry,
you.
more on
please.
the data engineer. Yeah, yeah.
Sorry, I want to ask if you are dealing with a organization like want to do project now and want to do you have organized you are dealing with you want to do project concerning a particular organization. Can't we approach the organization to get or to give us to grant us access to their data bank or database?
Yes, yes, you can do that. You can do that. So it depends on how sensitive the company's data is. The company, if they want to model and they see some value in what you are doing for them, if it will save them millions of naira, for example, or even billions, they will be willing to say, okay, we have a data warehouse here, you get access to it so that you can load the data and then build the model for us and also. So they'll give you access to it, of course. If you're an employee there too, they may give you a laptop such that you have secured access to the database, right? So yeah, it just depends. Yeah, they should give you access.
Because I asked the question because of based on where I'm working. Though
Okay,
I know I'm working in the airport, so I work with
okay.
immigration, but I'm not an immigration officer. And you see the passenger coming in and out of the country, when they do
Yeah,
their capturing, they have the biometric for them. So they have, I mean, there's a database that all those biometric goes to. So, and there
yeah.
should be a database bank. So if I want to do any
Yes,
project, at least I should be able to talk to them in the IT department and say, okay, I need access to your database so as to do something
yes.
for you and all that. So, and I want to believe that it should be the same for any other organization that somebody wants to do a modeling
To
for use machine language and learning to do something for.
yes, yes, very true. Very true. Yeah. Yeah. There are some data they call personal information though. Like biometric may be personal information where it will be very tricky for companies to release that kind of data, but
And
because there
but we
may be
can
legal
get
issues.
influx of
Inflow
foreigners,
countries they go to.
foreign
Yes, exactly.
foreigner, the movement of the
Hmm.
airline, how many airline comes to Nigeria to the airport here in a day, and in a
Exactly.
week, then the
Yes.
country they go, which of the country does people goes to mostly, in a month, in a
Yes.
year, maybe where they go to
Yes.
vacation, who are the people coming for business trip and
In
all that. There
fact,
are so many things that do information you can do
the
apart from their personal information that you can do. The inflows of movement. So
mm-hmm.
I think
Exactly.
that's
That
what
would
I
be
think.
very, very interesting. True, true. True, that would be very interesting. Okay, so we're going to look at maybe we'll do a simple car pricing prediction model today because we started our analytics with a car project. So we're going to just build some models and then see see a kind of template of how your project will look like. Maybe this will be more helpful for Gbenga. Okay, so we introduced supervised learning before in the previous classes that supervised learning is we're learning from labeled data. So labeled data means the data has a label for the particular output that you're looking for. I'm going to explain with this diagram here. So also supervised learning can be regression or classification problems. Regression problems, you're trying to predict a continuous target like housing price, like car price, like age or something, continuous or numeric targets, maybe not just continuous, but numeric targets, right? While classification problems predict mainly categorical variables. So you're trying to classify if an email is a fraud or not, trying to classify if somebody has a health issue or not. So those are classification problems. Okay, so when you are modeling and doing supervised learning problems, let's say we have a car pricing problem. We have these cars here, we know their prices. So this price is 5 million, 7 million, 2 million. These are the labels. So this data comes with a label of the prices that we're trying to predict. So with that, we're going to train the model and we train our model. Then we'll have an output called a model, and that model can predict for us if we give it any car, it will predict based on what was trained, based on what it understood from all of this data that we passed through it. So for example, this model can predict and say, oh, this car, it looks like, if you give it this car, it may say, oh, it looks like one of the cars I saw before. It's the price about 1.8 million. It doesn't necessarily have to be exact, but it's close and gives you a good prediction that makes sense, right? So that's supervised learning. There's the label data, can be regression problem, classification problems, and when you get the input, you train, and then you get an output which you can use to predict. So let's look at the simple car price. I just created this simple linear regression to help you understand what's going on in the background when you're building a machine learning model. So let's say we have a data. So this data, we're trying to predict car prices. And for this data, we have the number of doors. And for a car, depending on the number of doors, we can know the price. For a car that has one door, we say, oh, the car is about 7 million naira. For a car that has two doors, the price is about 9 million. For four doors, the price is about 13 million. Six doors, about 17 million. Now, so we're going to talk here. If we use this line, these are the points. So these are the points of this number of doors and price. So number of doors is 1, the price is 7 million. You see the plot here. When the number of doors is 2, the price is 9 million. You see the plot here. When the number of doors 4, 13, you see the plot here. So these dotted points are the plots of the data that we have here. Now, if we use this line to say, okay, it looks like this data point follow this line. Does this line make sense? Does it give a good approximation of this data? Can someone comment, please?
No.
No, sir.
No, why do you say no?
Because it's not in a straight line with the plots. The line
Okay.
deviates from the plots.
There's no
Okay.
linear relationship between them.
Okay, thank you very much. The line is far from this dotted point. The line is far from this point. So if you go further, you see that this line here is saying when the car number of doors is 7, you are going to get 6 million naira for the car. And if you look at all of these points, it doesn't make sense. It looks like when you have more doors, the price is high. But now we're getting 7 doors and the price is even lower than 1 door. So this model has some issues, right? So let's go for another model and see. Does this one make sense too?
It's even far. It's even worse than the other one.
Why is it worse?
No, sir.
Okay, it was because this is now showing even an inverse relationship between car price and number of doors. So it's going this other way. Why we know the price of the car is actually going upwards with number of doors. So this one here is predicting that when you have 7 doors, you're going to get 2 million naira for that car. So this is also a bad plot. This is also a bad fit. But if you go to this now, when we get a good line of best fit, it's called line of best fit because it's close to the data points. It's not too far from the data points. You will see that with this line, if we draw it further up, it's likely that when the car hits 7, when this line hits 7 here, you're going to get about 19 million naira for that car, which makes sense based on the data that we have here. So when you are solving a machine learning problem, the machine learning problem is looking at your data and trying to find a line of best fits. So there's some maths that's happening under the hood. There's some maths that's going on here. You are trying to optimize and reduce the distance between these points and this line of best fit. So there's some maths. You don't have to bother about the maths now, but I'll share a link with you if you want to do some further readings. So there's some kind of optimization we call gradient descent that's trying to descend, that's trying to reduce the distance between this line and this point. So don't worry about the maths, just understand the the model and how it's working. Now, so that brings us to the point where if we're trying to reduce the line, the distance between this point, these lines, and the line and the points here, it means that to select our model, we're going to do something called model evaluation. So model evaluation provides metrics for assessing the performance of a model. So the other inverse model, the other low model, and then this straight line, there has to be a way for us to measure if which model really if a model really performs well, right? So regression models are usually evaluated in metrics such as, there are metrics called mean absolute error, root mean squared error, mean absolute percentage error, or coefficient of determination called R squared. So these are different metrics. For the error metric, which are mean absolute error, root mean squared error, usually the lower it is, the better. So it means that there's a small distance between your line of best fit and the data point. Coefficient of determination, R squared just checks if your line is moving in the same direction as your data, and the higher it is, the better. Then all of these metrics measure, like I said, the distance between your data points and the model predictions. Okay. Now let's look at this data. Let's look at let's try to do a simple exercise here to look at a more complex model. So now we have several cars here, right? This is 7 million naira. This is 5 million naira. This is 6 million, 13 million, 5 million. If you look at these cars here, it looks like buses are around like 6 million. And this buses has maybe like 6 doors or 4 doors or whatever. Then it also looks like a car that has maybe open roof and is painted. It looks like they are very expensive, maybe like Lamborghini or something, or Porsche or whatever. It's 13 million naira. Then this one that looks like a simple SUV police car is 5 million. Then this is like also 5 million. They look similar. So based on looking at the cars, we could tell the different prices by looking at, okay, some features of the car. So what are some other features of the car that we can look at to be able to make some sense of the price? Just as humans, not looking at it as a machine learning model now. If you look at these cars and you're looking at the different prices, what are some features you'll be looking at that makes this price different for these different cars? What are some features that will come to mind for you to check to know why the prices are different?
I think the year the car was manufactured.
Interesting. Thank you very much. So you look at, maybe cars that are more recent may be more pricey. Why cars that are old may not be too pricey, right? So looking at the age of the car, the year the car was manufactured. Thank you. Any other thing?
Then you can look at maybe do call the portability of the car? How portable the car is.
How portable it is, the size of the car weight, yes. Yes. Yes, so that's portability. Like this one, it looks like, it's very posh and just simple. So maybe those kind of cars are very expensive. Any other, maybe we can take one more. Maybe you look at the power rating of the car. Like I put some things here. So when you get a project, you get your data, things you're going to be looking out for are called features that can enhance your prediction, things that can help you predict better. So feature, and it's called feature engineering when you try to select features or create attributes that can help you predict better. So like for the car example, we said we can look at the year of production, we can look at the design, if it's an SUV, sedan, or bus. They can look at the number of doors, we can look at the power rating, the engine size, and car width. All of these things are called features, right? So some of these features may come in as categorical variables, like the car brand there will be a categorical variable. The year of production will be a numerical variable. The number of doors will be a numerical variable, but the design here would also be a categorical variable. So all of these categorical variables and numerical variables, there are different ways that you can deal with them to get some kind of features that can help your prediction model. Today, we'll just focus more on just numerical variables. Next week, we can talk on categorical variables. So before we go into our practice for today, before we go to the notebook, first, there are steps in building a machine learning model. We've talked about data collection and cleaning. So we did some kind of data cleaning and exploratory data analysis last week. So that's step one. Step two also, which is a form of exploratory data analysis also, is the processing of your data, doing some feature engineering, then selecting your target variable. Your target variable is the variable that you are targeting. What are you trying to predict? Based on the business case, based on what the company has told you, what is that key variable that if you can predict it will improve their business? So that's your target variable. Like for the examples we just did right now, the target variable is the price of the car. Other things that we quoted as features, we use those features to predict the target variable. So if you have a target variable, to measure how well your model is doing, you can split your data to a training set and a test set. So you would train your model on the training set. Then you are going to test if your model is doing well by giving it some data that the model has not seen before. Because if you only train the model on training data, the model may just learn. There are some models that may just learn only about that training set that it has seen before, and then it will overfit that data. So when it sees a new data, it may not even understand it. Like let's give an example here. Let's say we have a model that let me just draw something here now. Okay, let's say we have a model that learns this. It says, you know what, I'm going to go from this data point to this data point to this data point. So you see that this line touches all of the points here, touches this point, touches this point. So if you won't check the error, you may find that if you check the error just on the training set, you may find that it's a perfect model, 100%, no error at all. But would this be a good model? Can someone comment on why this will not be a good model, this red line?
I think it's going to be a good
The line is
model.
not linear.
Okay. Okay. Someone said it's going to be a good model. Someone said the line is not linear. Good. Any other comment? Why is it not a good model if the line is not linear? But it predicts all the points.
Yeah, but if there are other points within, it won't give the right distance. Like let's say that the car pricing, then look at that, look at 3 and 10, give something that is not true actually. But
Yeah.
if you give exactly the distance, yeah, it might give you based on the curve because they are touching. But within the other points, because these are numeric variables. So let's assume other numbers like 3 or
Yes.
let's say 5. Yeah, they don't give us the actual distance.
Yes. So thank you very much for highlighting that. So this model learned very well the training set, but it will not do well on data that it has not seen before. Because if you give it 3 now, it's going to be predicting something else here instead of this point here. It's going to be predicting up here, right? Instead of this point here. So that's why you have to split your data into training sets and test sets so that you can check if the model is actually learning properly, if it's giving your best with this kind of problem here where your model just learns all the points, does well only on the training set, is called overfitting. So to avoid overfitting, that's why you would do. To avoid overfitting, that's why it's good to do test and test set. The other way is to overcome overfitting, but we don't have to go into too much details on it. Okay, so
Can someone mute?
Olamide, or is that? Olamide.
I'm coming, let me check for the person. Is it muted now? Okay. 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 So we talked about splitting the training set and the test set. You see why this is important. Then you will fit your model on the training data on the train set. Then once you have fit the model, you are going to predict the target variable for the test set using that train model. Then you evaluate the model on the test set to see if the model does well. So these are the very general steps for building a machine learning model. Data collection, pre-processing, split to your test and training set, then you fit your model, note this word fit, then you predict, note this word predict, then you evaluate the model using all the different error metrics. Okay, so now then finally there are some machine learning models for regression problems. You can use multiple linear regression, decision trees, random forest, XGBoost regressor. So these are different models. They have different mathematics behind them, right? Our decision trees just use simple yes and no methods for training on the data, but there's some complex maths going on, Danny. We don't need to go into those details for this class. We are basically going to use Python to train the models. At least we understand the general problem that we're trying to solve. But you don't need to go into it's only maybe when if you are preparing for an interview for a company that if the company is going to ask you all of these details, that's when you may need to study the different models. Like so we're going to build a car pricing model in Python now. You can check this link to go through more details about different models. I think this link is very simple. They try to put very simple both the Python code and explaining the model. So if you like maths and you want to just go through the maths behind it, you can check this link or check other links so that I can explain it to you. Random forests are just multiple decision trees, right? Then XGBoost use some method for optimization that's different from random forest, but it's still like an advanced decision tree also. Yeah. So let's go to our Python notebook. Let's go to our Python notebook. So if you want to follow the Python notebook now, I'm going to just drop the notebook on the group chat, on the WhatsApp group chat. I'm going to drop the notebook on the WhatsApp group chat so you can download it from there and also follow. Let me see. I'm coming. Just 1 minute, please. I think. Let me share. Okay, can you see the notebook now? Can you guys see the notebook?
Yes.
Are you with me? Yeah. Okay, thank you. Let me share this notebook on the WhatsApp group. Just 1 minute. Almost done here. So those who want to follow, you can now follow. Dropped it on the group chats. So let's get back to. Okay, so the data we're using today is a car pricing project. So let's read the problem to understand. So the problem statement here is that there is a Chinese automobile company that wants to enter the US market to set up a manufacturing unit for producing cars. So they're going to compete with some US and European companies. So they have contracted an automobile company. Let's say they have come to you and they want to understand the factors on which pricing of cars depends. They want to know what are the key factors that determine the price of cars. And specifically, they want to understand the pricing of cars in the American market, right? Since for the Chinese market, the pricing may be different, and well, the factors that also determine that price may be different, right? So you're going to now build a model to find what variables are important, and you're going to build a model to find if you can get a very good prediction of a car price depending on those different factors, right? So this is the business goal here. You're required to build a model to price the cars with the available variables, available data. It should be used to understand how exactly prices vary with these independent variables. Then they can now, with those on that understanding of the key things that determine the price of a car, they cannot build a business strategy around that to manipulate the design of their cars and then give a price that is competitive so that they can now compete properly with the US and European counterparts within the US, within the American market. Does that make sense? Does that make sense to you guys?
Yes.
Okay. Okay, so this is a clear case of, this is a clear business case where you apply a machine learning problem to help a company. It's a clear business case. And some projects like this, companies can pay as much as $500,000 or $1 million to consulting companies just to do this kind of analysis for them. Right? But of course, because it may be a large scale project, if you are paying that kind of amount, there may be more data, there may be more variables than just the simple data we have here. Okay, but let's look at our data. Let's get our data. We'll first load our NumPy and pandas. We're mainly using pandas. We're using pd.read.csv to load the data. Then the major Python package you said in the last class that you use for analyzing your getting your models and for getting the machine learning models that you would use in building is called scikit-learn or sklearn. The package you use for data analysis is called pandas. So we're going to use scikit-learn to pre-process our data. We're going to use scikit-learn to split our data to train and test sets. We're going to use scikit-learn to run linear regression and some other models that we pointed out before. So we're also going to use scikit-learn to score our data, to score our models. So our to score here is the coefficient of determination we talked about. Okay, any questions so far? Any questions from anyone? Okay, no questions means we're good to go. Okay, so let's check our data here. Let's see df.ed. What we talked about before, we said you can use the car brand to determine price. You can use the drive wheel, engine location, wheelbase, so engine size, stroke, compression ratio, horsepower of the car, peak RPM, all of these different values, you can use them to make your prediction. So we did some data analysis similar to this last week. And I think we also did some of this in the physical class. So we don't have to spend too much time on exploratory data analysis today. So if you just go through the data, you can see the data types. Luckily for us, our data does not have any missing values. It's just 205 points. All of the rows do not have any missing values. But if you have missing values, that's where you now need to like think about how to handle missing values. That's feature engineering. You may delete those rows where they are missing values. You may delete the columns. If there are columns that have a lot of missing values, you can delete them. But we just want to start simple today, and thankfully we do not have any missing data. You can check the number. You can check the number of unique values. Okay, you can check the number of unique values within your data. Okay. Then you can also describe and view some of the different values for all the different numeric variables. You can use describe to see the mean. We talked about this last class, the standard deviation, the minimum, all of those things there. Okay, so we can already observe from this basic thing that we've done that the database has no null values. If you look at the data types, we have about 10 string or categorical values. We have about 10 categorical columns, and we have about 18 numeric columns. Now let's do some bit of data cleaning. So we're going to drop car ID because car ID is just unique 205. It's just a unique serial number like the last data we used. It's just a serial number, so you can delete that. You can drop that. You can drop that. Any questions so far?
I want to ask, is there any advantage of dropping some of them? Does it make the model more efficient, like fast, or like, I don't know?
Question, good question. Yeah, so for you, like there are different reasons why you can drop different rows, right? Different columns rather. So this column, we're only dropping it because it's just numbers. It's just serial numbers, car ID. So the car ID would not improve our model in any way because it's not really varying with price. It's just a number 1, 2, 3, 4, 5. It's just nothing. It won't help us at all. Right. So there are sometimes though, which we're going to do that here. There are sometimes where there are some columns that may not really help your prediction, especially if they don't have any relationship with price. So sometimes you can identify that, you can take out those columns. That's still some kind of feature engineering. And of course, the more columns you have, the more it may take, your model may take more time to run to really learn something. So sometimes it makes more sense to reduce the columns and just focus on the columns that are most important. That's the features that are most important. Or it makes sense to also you can even sometimes you can even do what they call dimensionality reduction. So you can reduce the number of features you have so that you can just focus on the principal components of your columns and use that for prediction. But those that don't understand, you don't really have to bother about that for now. Let's just build a simple model and then do the prediction. Let's see. Is it clear? Did I answer your question?
Yes, sir. Yes, sir.
Okay, thank you. All right, so we're dropping this. Oh, shoot, I already dropped it before. I already dropped it, so I don't like to see all these errors. Okay, so okay, I'll just leave that. Okay. So then the car name, we want to do some exploratory data analysis here. So in Python, you can split I think we did this in the last class, or I did it myself before coming on the class. So you can split a string. This column is a string in Panda, so you can split it just by the space between the the string, right? And then take the first value there, which is 0. So if we look at that column, there are different car names: Alfa Romero Giulia, Alfa Romero Audi 100. So we just want to take the Audi Toyota. Let's see which product is really popular in the US market. Is it Toyota? Is it Audi? Is it Mazda? Is it Mercedes-Benz? So we'll just split the string and take the first value there. So change that to the car name. So if we check the unique car names now, we can see all the different products: Audi, BMW, Chevrolet, Dodge, Honda, Isuzu. The last class we had Isuzu, then Isuzu, I capital letters. But this one now, it seems like Mazda and Mazda is an issue. Nissan and Nissan is an issue. Porsche and Porsche. So Toyota and Toyota. So when you do some of these things, like when you split, like you can see some areas where you need to clean. So we need to clean that data now so that we can get a proper spelling for all of these different names. So if you clean that, you can use replace. We use replace here, or we did something like this in the last class. So we're just replacing Mazda with Mazda, Nissan small letter with capital letter. So these are just replacements here. And we're assigning that back to car name. So if you run this now, then that's replaced. One of the colon symboling, it has a data type of integer, right? But it's actually a categorical variable of the symbols. So we have to change that, the symbols for the car, whether it's 3, 2, or 1. So we change that to categorical variable. Then now we want to, because I said we're going to focus more on numerical colons for this analysis today. Maybe by the next week we'll work on how to deal with categorical colons. Because if you notice, categorical columns are just strings, they are text. A machine learning model would not know what to do with that, right? Pandas will not know, scikit-learn or Python would not know what to do with a string rather. Without to use, there are some models. There's one model that you can use this categorical variables directly. But for most of the models, you may need to convert this to a number that the computer can read and relate to and use that to predict. So in Python, we can separate the numerical columns and the categorical columns. So we're going to separate that here. So we use the keyword here, exclude objects, columns that are tagged as object, that their data types are objects. So we're excluding that to get the numerical columns, and we're including columns that have object as categorical column. So that will help us fast track our analysis. Any comments or questions so far?
Yes, I have a question.
Please go ahead.
Does it mean that you need to, assuming you have car, Toyota, I mean, they give you data that is all string. All the data, you have to convert them to figures. And when you convert it to figures, how do you now differentiate to know which one is which? Or will it just generate a specific number for each string? Will each string, assuming they give me a name of a car as a Toyota, that I need to convert to convert to numerical data. Will I now change that particular Toyota to string to give me a number, maybe like 1 to represent that Toyota string they gave to me?
Good question. So you already have an idea, right? That you can just make Toyota, anywhere you see Toyota, it can be 1 or 100, it can be 10 or anything, but that number will be consistent for anywhere you see Toyota. Okay. You can make Nissan like that also. Yeah, that's called label encoding. Okay. So that's just one way to deal with categorical variables.
Okay.
right? So we're going to talk about that next week, hopefully.
All right.
Now, another way to deal with it is called one-hot encoding. But let's not go into that for today. I think we're taking a lot today, so let's not bore everyone with too much of those other details. Yeah, but intuitively, rather, you're already getting the clue on how you can handle some of these things. You just assign a number anywhere you see Toyota, you call it that number. Okay, but what we see here now, it's already clear from this mini data. What did I just do? Let me check. I think the car name was not changed properly. Let me change it here. So do we have, oh, I did not run this row. I did not run this. Okay. Let me run this. Okay, so that I missed running that replacement. So you see how messy it would have looked like if we did not do these splits to just make more sense of these car names. So, but when we made more sense of it, we can see that Toyota is very popular in the US market, followed by Nissan. Wow. Then Mazda, Mitsubishi, Volkswagen. If they do this in Nigeria, which car product do you think would be top? Top two would be what in Nigeria?
Toyota.
Toyota.
Honda.
Toyota.
Honda, okay.
Honda is northern
Yeah.
car. Toyota is the leading car in Nigeria. Honda is
Toyota
northern car.
is the one that is most popular.
Yes. Sir.
Okay. Wow. Okay. So it's Toyota, then I think maybe Honda, then maybe Benz. So maybe Benz will still come up.
In fact, Honda
Peugeot
is
used to
not
be
a common
popular.
car. It's
And
just
And
in
also,
the north.
all this Vanagon, this Volkswagen, Vanagon for transporters.
Okay, but Volkswagen, yeah. So in the US market, it's still Toyota, then Nissan, Mazda, no, yeah. So that's it. Then we can also look at the price. Price is like a histogram plot. Just so this one we're just looking at an histogram plot. So the hist plot is like a frequency plot. So we're looking at the distribution of the prices. So between 5,000 to maybe $10,000, you can see how many cars are within that price range. So there are a few cars that are above $40,000, 35,000. Most of the cars are around 5,000, 10,000. So maybe the 25th percentile would be around maybe between 10,000 and 15,000. Let's confirm that from here. Where's the price? Okay, so, okay, it's even less than 10,000. 25th percentile is about 7,708. Right, so it means about about 75% of the cars are above that price range. Okay, so let's go. Now we talked about doing correlations also. We can look at features that move in the same direction with correlation plots. So the correlation map, we did the heat map last week. So let's look at one interesting rule here. We're trying to predict price. So for price, which of these car features have a good relationship with price? Can you look at this price row here and check which of this car? So if you look at wheelbase, for example, it's 0.58. So it has it's not too strong, but it has a above 50% relationship with price. The car length has about 68%, 0.68. But the ones that have very strong correlation with the car price is car width, 0.76, curb width, 0.84, engine size, 0.87, horsepower, 0.81, then maybe highway 0.7, then city MPG. So all of these things are, these numeric variables here are key, maybe very good predictors of price since they have a good correlation with price. Does that make sense? So any questions?
Yes, sir. Is it the high? Is it the highest that has the relationship, the correlation, or the lower it gets?
Yeah, yeah. So it's not really mm, it's not really just the highest or the lowest, because if it's very negative, it's just at the ones that are at the maybe as close to 1 or close to -1, because correlation is between -1 and +1. So if it's close to -1, it means there's also a strong relationship, but they are moving in opposite directions. There's an inverse relationship. So if car price is high, that particular value is very low. So that's like we see that for this highway MPG here, -0.7, and city MPG -0.69. Ahead. But when the both of them are high, like when it's 0.87, for example, engine size, it means that both of them are moving strongly in the same direction. If the engine size is high, then the car price will also be high. So if it's close to 1 or if it's close to -1, you can define or understand the relationship there. So this finding here, it shows that car weight have a positive correlation with price. But we are also observing now also that there are some negative correlation that could also show a strong relationship with price. Okay, so we can also look at the box plots. Just run this again. You can also look at the box plots. Box plots, I don't find box plots too interesting anymore. But they give you an idea of where there may be outliers and then the relationship between price and some of these features there. So we're checking the relationship between each of those values, door number and price, foil type and price, each of the variables within that, right? Door number 2 and 4, usually they have almost the same price, but it looks like when you have a higher door number, you have a slightly higher average price than 2 doors. Then let's see diesel. Let's see the diesel foil type. For the foil type, let's see the foil type there. Okay, foil type, the diesel engines have a slightly higher average price also than gas. So looking at the box plot, there may be some relationship that you can tell for especially for the categorical variables, especially for these categorical variables. So there's a method, though you don't have to do this. You don't have to do this feature selection, right? You know, just now we're talking about selecting the best features to use. We're talking about selecting the best features to use. You don't have to do this. Yeah. So you don't have to do this, but usually you can do it also. Like feature selection is just selecting the most critical features that would help you in predicting price. That will help you in predicting price. Sometimes you may have so many features you may not be able to select automatically and all, but then it's a good step. It's a good thing to select the key features that can help you predict correctly. So let's focus on so now we want to create our training sets and our test sets. But first, let's define our x's. Our x would be we're using all the numerical columns for prediction, and we want to make price. We're going to drop price because we're going to make price our target variable, which is y. So if we do this, let me see how X and Y looks like. X. So you see here that X is just all the numerical variables, wheelbase, car length, car weight, stroke, all of these ones. Then if you look at Y, our Y here, is just the price. So Y is just the price. Okay. So now we want to use a random forest regressor. There's a method in random forest that can help us select some features. So we want to select the top 5 features that would improve the prediction of price. So we're going to fit those fits. We're going to just fit X and Y to all the data. We have not done our training set and test set yet, but we just want to select the best models that can help us predict price better. So we're going to use random forest for that. So with random forest regressor, we can select the number of features that gives us the best prediction. So if we check the support of that features, we would get the top features that give us the best prediction. You don't have to bother much about this. It just helps us, like we said before, this would help us improve our prediction. So maybe a good step for your project also. So you can check for other methods. Maybe we'll touch this. Other methods of feature selection. Feature selection. So if you look at it now, we'll see that most of is selecting the top 5 models that we can use, features that we can use: car weight, curb width, engine size, horsepower, and highway MPG. If you look at this highway MPG that I pointed out here, highway MPG, I think it had like a negative correlation. But it's saying, even though it has a negative correlation, it's saying that there's a strong inverse relation, so we can actually use it to still predict price. So it's not only positive, strong correlation that it will use. It picks some positive, strong correlations here, but it also picks this one that is negative as a very good feature that we can use to predict price. So we have 5 features here that we can use. So now we can focus on those 5 features and just use that for our predictions. This pair plot takes time to plot. So we just want to see the plot of these features relative to one another. You can see that most of them have strong correlation, moving in the same direction. Okay, engine size has a different correlation with, an inverse correlation with highway MPG. So now we want to build the models. Let's first do linear regression. So you see all of the things that we'll be talking about. These are the key steps that you will do for your project. Okay, no, we won't talk about that. Okay, so these are the key steps that you will use for your project. But realize first that for building machine learning models, usually you will spend more time just understanding your data and then selecting the right features, preparing your data. You may spend about 60% of your time just on understanding your data, right? Then maybe 20% of the time building your model. Then the other 20% may be improving your model to make a good prediction, right? So for this now, we have our X. We've said we want to use just the top 5 features here, which are X. We want to use just the top 5. Let me run this and let's look at X now. Let's look at what X would be now. X would just be those top 5 features that we selected with our feature selection method. So these are the top 5 methods. That's our X. Then we said that you can split your data using scikit-learn train test split. We want to split our data to X train and Y train. So X test and Y test. So who can tell us, let me know if you are following, who can tell us why we are using X train and Y train, then X test and Y test? Who can tell us why we're using X train, we have Y train, X test, then we have Y test?
I think we in such a way that so that we won't cheat the model. So you want to separate them in such a way that you use some for your training and then you use different data completely for the testing based on what you explained that time.
Okay, good. Thank you very much. Any other person wants to add to that?
We are using it to get a good fit, best fit for the training model.
Okay, good. Thank you. So what is X train for the training set, for example? What's X train and what is Y train? What is X train and what would be Y train?
X trend will be the other features, while the Y trend will be the price.
The price.
So, yeah.
Good. So X train will be the features for the training set. Then
And the
Y
white
train would be the price for the training set. Okay. So one thing you have to observe also, let me just highlight this here, keep this in mind for your project, is that you see that these values here are random rows. These are the row numbers from the table, from the original X table. These are random rows. 163, 64. So you just pick random rows for preparing the data. Before I comment, let's also just discuss, why do you think the model is we're shuffling the data? Why do you think we're shuffling the data before we run the model, before we fit the model?
I think based on what you explained and the other this is for us to we don't want to just carry some data because of how they are more related. So if we randomly pick some of them, it will better. It won't cheat. Let me use that word. We might not be able to cheat the model. So it will be better to get a random this thing like from different areas so that some are closely related, maybe based on some during the this thing. Don't know.
Okay, that makes sense. Yeah. Thank you. Any other person wants to add to that?
I think we do that to eliminate what we don't need in the data.
It's all the data that you have there. You just shuffle it. It's still the data. Okay, so yeah, so both contributions add to what we're really doing here. It's such that so that the modelers can see as much as possible within your data, because let's say if you have an ordered data, let's say the top, we want to split the model to, let's say, 153 rows, and then I think the test set maybe maybe 50 rows or so, because 205 rows, right? So let's say the first top 153 rows are just about Toyota, then maybe some Honda. Then your model will only learn about Toyota and Honda. Then maybe the test set, you will now be showing your model for the test set. You will now start showing your model Mitsubishi or the other cars, the Porsche or whatever, right? No. Okay, so Porsche. So it means that your model will only see this for training, but then it may now start seeing Porsche or new car products in the test set. So your model will not learn much about this test set. So it's better for some cases, like you can't do this for time series because time series is ordered, right? The Monday data must come before Tuesday, before Wednesday. So that's time series on. But this one is, you want your model to see as much as possible Toyota, Honda, Mitsubishi, Peugeot. So you just shuffle it so that the model can see some sort of random data or see most of the different categories within your data. So it's similar to what you guys said. So that would improve the fit. That would improve your prediction. It will improve your prediction because I remember one time someone I was working with in machine learning, she just put the model together. She didn't do any shuffling. When she started testing, saw that the model wasn't doing well. She was surprised. Like, what's going on here? The model did well accurately for a training set. So there was overfitting for the training set. But when it got to prediction now, testing just saw that the thing wasn't working well at all. So we now found that she needed to shuffle the data to get a better representation of all the data, all the categories within the data. So we have created our training set now, and we have created our test set using scikit-learn train test split. So let's go to linear regression first. Sorry, we're almost done. So we said that for yes, please.
Like during the training, the amount of data used for training and the amount of data used for testing, does they matter? Like, I don't.
Good question. Yeah. It matters. It matters actually. If there's not so much variability, if your data is not too, there's no large variance within your data, a small data set may help, right? Just maybe not too small, but for most machine learning models, the more data you have, the better. So you need as much data as possible. The more data you have, the better. Like I won't say for a recommender system. Let's say let's say like ChatGPT. Let's say like ChatGPT, for example, that platform that's this platform that helps with so that platform that helps with dealing with what do you call it now? Chatting, where you ask the question. That's my ChatGPT platform there. Different you can ask a different question to give you answers there, right? Okay, so if you with ChatGPT, you need enough data to teach the computer how to understand language. You need enough data to teach the computer how to relate with a question and then reply back. So that data, like some models have about 4 billion parameters. Some of the models that they use in building ChatGPT, like Facebook has one too, Llama 2, I think they call it. So for most machine learning models, especially for like language processing, generative AI stuff, like you have what do you call this one now? Image processing, video generation, data, all of this, you need a lot of data points. But sometimes for company data, you may just, if you get like, maybe you should be looking at maybe like 10,000 data points, you may be good to go. This is just a simple case. That's why the model may do well for just this simple 205 data points. Yeah. I hope that answered your question.
Yeah, you answer like 80%.
What's the other 20%?
And the 20 is like now that I have my model, so I have all the data. So like, what quantity should I divide for my test, and what quantity should I divide for my training?
Oh,
so should I
okay.
give more data? Should I give more of the data for my testing, or should I give more of the data for my training?
No, you give more of the data for your training. For your training. Like this one, I think 80%. I think for scikit-learn, the default is 80-20. 80-20, or is it 70-30 in this case? Let's see. 153. Yeah, it looks like 75-25%. So usually you would give more 80-20, 75-25, or 70-30. So you give more percentage to training than testing. Yes, because you want your data to see your model to see as much as possible, to learn as much as possible. Then use some random some other cases to just test the model.
Yes, sir. Thank you.
Okay. Yeah, if you wanted to say something.
Yes, sir. I wanted to ask the test data, is it going to be from like just what you said now, the random? Are you going to bring it from outside the data set, or is it going to be part of the data that you already uploaded before? Is it going to come from the CSV file that you loaded, or is it going to
Yes.
be a generic something?
No, it's coming from the data we loaded. So we loaded that data to DF.
Okay.
Right? So that data is in DF. So I've put df.price to Y. Right? So the Y here is the price column. Then X here is the DF, the columns that we selected from our feature selection. So we selected those columns, feature, and then we put that in X. So then we now use this string text test split to split X and Y.
Okay.
Yeah,
Okay.
so X and Y is from that data set that we loaded. This random state here is just selected to, so usually in Python can select any random state, and give you different values every time you run this. It will give you different value if you run this every time without random state. So you specify the random state number, Python will give you specific random values every time you run this. That's why you see random states here.
Okay.
Sir,
But it's not compulsory.
okay. I want to ask a
Yeah, go
question.
ahead. Yeah.
The DF now that is there a price part of the DF? Because when you were taking the X, like the first, based on the Python that we were doing, like the first Y equals to DF dot price, I know that okay, you are trying to get the X price.
Price.
So what of
Yeah.
the X now? The futures, are they like element we didn't drop price when we're taking the futures? That's for the
This
X.
one.
No,
This
for the
one.
okay. All right. So okay,
No.
I've seen.
Yeah. Okay. Because feature is just those 5 columns that we selected. That's why.
Okay, sir. All right.
Yeah, those 5 columns. See them here. So if you put that in the data frame, it just selects these 5 columns. Car weight,
Okay,
curb
sir.
weight, engine size, or switch. Yeah.
All right. Thank you.
Well, sir, is there any situation where the random state can equal 1 instead of 0, or any other number?
No, you can put any other number, any number here. Any number is fine.
Okay.
Maybe not too high, I don't know. But you can use we can use 10, you can use anything. I'm just trying not to change our conclusion. Oh.
Okay, sir.
Yeah, I'm just trying not to change the conclusion we have, because if you use a different if you shuffle the data and use a different set of numbers, for example, the model may learn differently and your result may be different. So those randomness sometimes can make your model just fluctuates different. So if let's say as we use 0 here, maybe we'll try it. After we use 0, we'll pick for another model, another random state, and see. But yeah, you can use any number. So far it's fixed. Sometimes in programming, when if you're going to deploy this, you will just set the random state somewhere at the top. So every time you have to use random state, you just use the same value down. Okay, so I want to do linear regression first. So first we'll import the model we're trying to use. It's linear regression model. So next we'll do linear regression. We'll call linear regression. So usually we're calling linear regression class here. So you can put some attributes. Linear regression may have some attributes. Let me see. So it has you can put number of job, fit intercept, bullet. So you can put different values here. It will explain fit intercept, true or false. Well, or you can just use the default value. We can use the default value. So default, you just call it without any parameters. Then once we build that model, then we can fit that model to our data. We said the next step is to fit the model. So when you're fitting, you're going to tell the model the training set. So we're giving it X train and Y train. Say, okay, help me, you're saying model 3, please help me fit X train and see if you can use it to predict Y train. So once the model is fit, then it has learned something from this data. So it means the model has been fitted to this data, it has learned something from this data. So now you can use it to predict. So you now say, okay, model, you know what, please help me predict S test. Let me see if you did well. So when you predict S test, you can now use that value to compare Y test. Because Y test is the original value you're expecting. This prediction here, S test is predicting some Y test values, prediction set. So yeah, you can now compare those two sets and say, okay, how far is this value? So this LRO test here is like the straight line that we're drawing just now. This is like that straight line. And Y test is like the dotted points of our S test data. Right? So you're not going to compare this and say, okay, what's the ROT score for this self? Let me see if you did well. You check that. Then you can also do mean absolute error. You can do mean percent, any other error metric. So let's run this table now and see. Let's run this cell and see. So it's saying our coefficient of determination is about 81% or 0.8162. Then the mean absolute error is about 2707. So one challenge you have with mean absolute error is that sometimes it's not easy to interpret. But let's interpret it and say, okay, you know what, this mean absolute error here, let's try to get a percentage value. We want to, this mean absolute error, we want to divide it by the mean of Y tests. No, not Y test now. Yeah, of Y test of the original set. The original set, so Y test. So we're going to just use this mean to divide the average value. Let's see if it will give us, if it makes sense. Let's see the percentage. So this is just, so the error is low, 20% error, 20% or 0.2. It's not too low though, it should be lower than this. But 2707, yeah, that's what we get for this, for linear regression. Any questions from these codes here so far? Any questions?
Yes, sir. I have a question. What's that LR score R equals R raised to power 2 or R2? Is this is it a function or is it a code? Where did it come from?
It came from the moon. Sorry, I'm just joking. So this R2 score, we when we're importing scikit-learn, let's go up. When we're importing scikit-learn values, we imported R2 score. See it here. So we said the metrics that we import R2 score to measure as one of the metrics that we use to measure our model's accuracy. Okay, so that's R2 score that we now apply there. So when you want to use a metric to measure you would give the metric the original set, then you give the metric the test set.
Okay.
So the original set is Y test, and the test set is what we predicted here. Then you compare the R2 score. So let's look at the other models. Let's look at this one. Decision tree. Why isn't decision tree regressor? I don't know if it's loaded already. Okay, we've loaded it. So decision tree regressor, we've loaded it from scikit-learn. Then you fit the same step. Then you predict. Then you compare the scores. Then you can get the mean absolute error. We're also going to do the, so this is 0.86. Let's also get the percentage mean absolute error. The lower the better, divided by the average, or doing mean of the Y test. So this is lesser, 0.16. So about 17% error. Let's even look at another thing let's look at Y test. Oh, I wish I can just concatenate this. So you see y test values here. Mm, you know what? Let me just create a data frame of this. I'm not sure if this is a data frame already. Let me just create a data frame. Okay, so this price. Let me call it DTRO tests frame or something. I want to put the results side by side. I want to put the results side by side. Then I'll call, what's the other one now? Prediction. Price prediction. Price prediction is DTRO test. So let's open our data frame and see how it looks like. So you see what the model predicted. For some price where you have like 6,795, so this particular car, the price will be 6,095. This car is 15,750, so it's going to be 18,000. So you see where we are getting that error of 16%. So usually the margin of error, if you check well, is just between that, maybe up to 20%. If you can add maybe almost 16% to this, you may get the gap or the distance between the price that it predicts and the actual value of the car, plus or minus. So you see the prediction that this model is giving us, saying this 20,000 car, it's about $21,000, right? $21,000. This is 31,000, say it's $36,000. So the model is not doing bad at all. Has given us a close range of the prices. This one is a bit far though, 9,000 and say 17,000. Not to try for that one. Okay, so let's go to that decision tree. Let's go to another model. I think the best model was random forest. So this random forest regressor, the same steps. Let's just run this and see. So this is 1820. Let's see the percentage error also for this, for the percentage mean, the mean percentage error, MAE divided by MP.mean y test. Oh, this one is much lower, 13%. 13%. So you can do the same thing for this to see how the predictions look like. Okay. Okay, SG boost is also high, but I think the best was this random forest, at least for this particular example. Okay, so that's an example of a car price prediction project for this company. That's an example here. So we've been able to build a model that predicts the car prices, and we're able to identify some key features that predict the car prices. We're able to measure, evaluate the model and find which model was best for us. So you can use that to tell the company some important details of what you found out. Like, okay, your model can predict with about 90% R2 score. Your model can predict with just about 16% margin, in 13% margin actually, in terms of the mean absolute error percentage. So, and then you have identified some key features that the company can use to determine their own price car. So they would put some key features within your model and then use that to determine the price, and then push that car to the market with that specific price that the model is giving. Or they may reduce the price to maybe 16%. Since there's 16% error, they can reduce the price by 16% from the model, or they will increase it by 16% also. Yeah. So that's it. Any questions as we wrap up? Any questions?
Yes, so what I want to ask is, we actually dealing with numerical data here, and
yes,
from the the beginning to the end of a model. It's just dealing with numerical data. I want to ask,
Yes.
what's the difference? Is this type of model, is it the same system that all those video generation models used to? Are they using the same model or the same approach in generating that kind of model? Like all those picture generating models and video generating model, do they use the same method?
So those video generation model, and so yeah, let me just give me 1 minute, please. Let me just get the, I think some parts, since we're wrapping up, let me just get the attendance list. That's an interesting question. Oh, that's an interesting question. Let me drop the link for the, so you can do your attendance here. I think it's this link. I've dropped the link on the chat. Yeah, interesting question. So you said the question is video generation and image generation, if it's the same kind of model they use, right?
Yes, sir.
Yes. So for text generation, it's different, right? Because there are some models for text generation. There are some specific models that are able to do some kind of let me not go into too much detail, but there's some kind of frequency generation to check if like if you say I am coming. So there's some kind of checking if I am coming always occur together in a text. So if it's always occur together, so the model begins to understand that, oh, it looks like this kind of statement makes sense. So I'm going to use that to also communicate with people. Or if someone is telling me this, if someone is telling me I am, if coming always comes after I am, then it will know that, okay, I am coming would be together, and then it can make sense of it, like knowing that, okay, it looks like I am always follows, a coming always follows I am. So there are some, they are even like that, they can use it for even music generation. So let's not go into that, but the image own can actually also be modeled with something like this. Because images, they are going to look at the pixel. They are going to, there's a way they can represent the images in terms of the pixels within the images. So you can represent the images as features. Then a particular image will have a particular target that, okay, if cat, let's just take for example, cat may be represented by some set of pixels that may be 64. For example, for one, maybe the height of the cat, it can represent it as 250, 2548. The whiskers of the cat may be represented by this, all of these different features, right? So you can now train a model to find out, okay, if this thing is combined together, it gives me a cat. Cats 1 or cats 2 or whatever. So those set of features, they can also be features that determine a dog. They can also be features that determine a car. So with all those different features now, you can now train a model to predict whether a particular image, depending on the combination of the pixels features, whether it's a cat, whether it's a dog, whether it's a car or anything like that. So I think there's also a similar thing going on for the natural language processing models, but it's a little bit, that language processing is a little bit more complex, right? Even the image now, I think they are now going into some kind of generative AI too for images. But on a basic level, it's still, most of these kind of models can still work for image processing. Let me not talk too much. Yeah, but thank you for the question. That's a good one. So when you are choosing your project, Yeah, when you're choosing your project, you don't want to encounter some very difficult stumbling block. You don't have to choose a image processing or natural language processing project. But if you find an interesting one, we can go into, we can look at it. If any of the groups or any individual find an interesting natural language processing or image processing project, we can look into it. Just the time that we have is very limited. I don't know if you can get much value within the time that we have. Yeah. Okay, any other questions? Oh, I think I should. Okay, so I'm going to stop recording now and stop sharing. Let me stop recording this.